Okay, let's take a look at example 13.9. We're going to be using normal, tangential, and binormal components. We're just normal and tangential in this problem. We are given the mass of 60 kilograms. The picture in the book draws a circular half pipe, but there's no such thing really. So we're looking at a circular portion of the half pipe. So the radius is constant along the path that he's traveling. He starts from rest at theta is equal to 0, so here's theta is equal to 0 up at the top, and that angle is going to go down to 60 degrees, and when it's at 60 we want to know what the normal force on the rider is. We're going to need the accelerations and analyze the forces at play to figure out what that normal force is. Okay, so first thing, let's make a Freebody diagram. So this is going to become my unit tangent direction at some point on the path. It doesn't have to be 60. Perpendicular to that, we have a normal component. And so here's our path then. Alright, our mass is right here. Remember, we make our coordinate system at the mass. We are going to have a normal force of the track pushing on the person or the skateboard, and then we need to project in this direction and project parallel to meet up with the weight mg. So now we have a right triangle. We can say this component of the weight is mg . This is going to be sine theta, and I'll show you why. Because theta equals 60 in this is not this angle. Check out the trigonometry and you'll find out that this is the angle we're interested in, which makes that mg sine theta and this mg cosine theta. Okay, what else do we have? That's it. That's going to give us an acceleration in the tangential direction, and we're curving on a path, so we're going to get some normal acceleration also. Alright, let's do Newton's second law and sum up the forces. If I sum up the forces in the normal direction, it's going to give me the mass times the acceleration in the normal direction. Remember, we can rewrite that acceleration as v squared over rho, or r in this case. And what kind of forces do we have? Well, I have a normal force pointed up. I have a minus mg sine theta going down. That's all going to equal the mass times v squared over r. Okay, let's sum the forces in the tangential direction now. And that's going to be mass times the acceleration in the tangent direction. I will have just the positive mg cosine theta. That's going to be equal to the mass times the acceleration in the tangent direction. So we can see that in the tangent direction we can get that the acceleration is g cosine theta right away. Alright, do not plug this in. Do not plug in 60 degrees yet. Okay, we have a function of theta. Acceleration is a function of theta right there. So, what should we do? Well, let's do UDV is equal to ADS. Now, you may say, well, I don't have a ds, I have a theta. So we need to go to the definition of an arc length. An arc length is equal to the angle in radians times the radius. If we take a time derivative, I get ds, or sorry, derivative with respect to theta, I get ds d theta. The derivative the derivative of theta just gives us a 1 and r is a constant. And then we can rearrange this to say ds is equal to r d theta. Now we're given r is 4 meters in the problem. We can go ahead and put that in here. Now this becomes our new ds. So v dv is equal to 4a times 4d theta. Now let's substitute the acceleration. I have g cosine theta. Let's pull the 4 out in front. And now we have the correct variable of integration. And we can carry this integral out. It started from rest, some velocity, and it started at some angle 0 to 60 degrees. That's where we plug in 60. Alright, what we get from this is Vf squared is equal to, it's like a 39.24 times the sine of 60 minus, this is over 2, minus the sine of 0. The sine of 60 is square root of 3 over 2. The sine of 0, or the y value at 0 degrees, is 0. So, moving the 2 on the other side gets rid of this 2, and I get Vf squared is equal to 39.24 times the square root of 3. So it's a radical. And let's keep it in Vf squared because we can enter Vf squared into that formula right there. So I'm going to copy this down. I have the normal force, so this was in the normal direction. The normal force minus mg sine theta is equal to the mass times v squared over r. Well, we have v squared, we can plug that in right away and rearrange for the normal force is what they asked for. So m times v squared over r plus mg sine theta, and we could factor an m out if we wanted to. But we get 1529.23 newtons. Alright, that's how hard your knees are pushing into the ground. That's how exactly equal to how hard the floor is pushing up on the skateboard and how hard the skateboard is pushing down on the floor on the ramp at that instant. Big thing though, this was not a constant acceleration. Don't use constant acceleration equations.